Nando. So my name is Hannele Hautinen. I work at the Technical Research Center in Finland. But the most thrilling project that I am working on is leading this international collaboration of Task 25, being the operating agent, 2 + 5 is 7, 007. Very thrilling. Well, not that thrilling, fortunately. But anyway, welcome all to this simulation talking about wind integration studies and recommendations. What we will do today is that I will start, or there will first be an introduction of the tasks by me and Markus from Task 14, the solar side. And then we will talk about these recommendations. So I will first go through the setup and the balancing and generation adequacy parts. Then Damien and Markus will talk about the grid parts, and this is the main upgrade that we had when we made the update of the recommended practices, the edition 2 that we are talking about today. So we will spend, sort of give them, or this part, considerable weight. And then we will, I will take over to conclude. So Markus, you can first start by introducing the solar side.
Yes, just a very short introduction for the IEA PVPS Task 14. PVPS stands for Photovoltaic Power System Program, and in Task 14 we are focusing on high penetration PV and electricity grid, so very related to the topic of PV grid integration. We're starting now this year with the third phase of the task. Title, quite ambitious, is Solar PV in a 100% renewable energy sources power system. And the motivation is, of course, to promote the use of grid-connected PV and also to reduce technical barriers we have. And here we have to address different kind of challenges in PV grid integration we are facing, and we're also discussing here different kind of solutions. And for example, PV systems have to provide additional services for the power system and for the energy management in order to achieve this kind of very high penetration levels. On the next slide, you just see some outcomes. So we are already in the third phase, so we already published a different kind of reports. So I recommend checking out the web page, which is shown at the end. So we're basically providing best practice examples from international perspective. We're providing state-of-the-art and also typical key methodologies for high PV penetration scenarios. So topics are, for example, grid interconnection studies and planning, how you deal with that, technical standards and interconnection requirements, and integration within the smart grid, so everything related to communication. Yeah. I just can highlight and recommend here checking out the webpage. There are already a couple of reports out there. Yeah, Hannele, back to you then.
Okay, so we are now showing the nice collaboration between 2 technical collaboration programs, the solar and the wind, and especially the grid integration task. So the Task 25 already started in 2006, and we also we are on our 5th phase, and we make several reports and summaries. So normally the results of integration studies you can find in different reports, but we are not discussing today. Today we are discussing the methodologies and the recommended practices, which you see a cover here. And we also do have fact sheets and even some hourly time series databases on our website. We started from comparing studies of wind integration, and during our work, we have more and more experience of wind integration, and also now wind and solar integration coming mostly from Europe, but also from US. And then I think that our work also has evolved to really look at renewable power system studies instead of only looking at integration. And also our focus is towards 100% renewable studies. Okay, so then going to the subject of today, the recommended practices report has been designed to go around this flow chart, which took a bit, how would I say, comprehensive, detailed, a bit complicated even. We are fully aware and state out that a complete study with links between phases, this is how we think it looks like, but no studies, of course, will analyze part of these impacts that wind and solar have, and also the goals and approaches will differ. But somehow to get a comprehensive view, what we are then doing here is that in blue, now for some reason I don't really get the, here, in blue we have the inputs and the setup of the study. And then in green we have the actual simulation part of the study, and we show a sort of recommended route also going here. So I am talking about these parts, and then Damien and Marcus are talking about the grid part, and then I will take over to then finish. So starting from the portfolio development and system management. So this is mainly to first think about what to study, the setup of the study. And we have learned that the main assumptions that we make in this setup phase will actually be very critical for the results, especially when we are looking at future systems. So how we add wind and solar, what is the remaining generation mix, what are the operational practices foreseen for future systems. These all have a very big impact on the results. So the very basic recommendation that we have from this stage is that when we are studying the first additions for wind and solar, it's okay to look at your the system that you have currently or you foresee in a couple of years. However, when you do have more wind and solar, it will be increasingly necessary and also beneficial to actually look at the portfolio of your generation and network and take into account potential flexibility and also the technical capabilities of power plants. So for future studies and for high shares of wind and solar, we highly recommend to have additional scenarios also for the operating practices. For the input data, we have gathered all the recommendations in this one table, which of course looks also quite detailed and comprehensive, a bit complicated perhaps, but what we basically, of course, always we cannot have too much input data, but however we have different models that have different model details, and for example, this capacity value part for the resource adequacy, the generation mix of future, there you have the possibility of not having so detailed sort of variability and smoothing impact of wind and solar. However, here you should have quite a lot of data, so long time series. Whereas when you look at the operation of your power system, the dispatch and the unit commitment, then you need to have 5-minute to hourly generation time series, and it's very important to have the forecasted time series and all the smoothing impact and all the time series, different time series here, and also more detail of your power plant, how they operate. For the grid part, usually up until now, they have mostly been taken just snapshots of either the previous phase or then just some general snapshots. But of course, we are now working towards having more and more events simulated also for the grid part. And there, of course, you also see a big difference in how the network will be simulated, what is the level of detail in these different parts of the study. Related to the system management, or the sort of the setup, is the operational practices, and what we have very often is the question of how wind and solar impact the operating reserve. And here we have quite clear recommendations that you should have time-synchronous data with wind and solar and load. And you should have the distributions of all your uncertainties. So you have uncertainties for generation outages, you have uncertainties for the for your load, the forecast errors there, and then you have here wind and also wind and solar forecast errors. So the right way to look at the impact of wind and solar is to combine these all and then check that your sort of loss of load probability or your confidence level, so to say, are at the same level before and after adding wind and solar. We also see that when you have larger shares of wind and solar, dynamic reserve setting is saving a lot of power system resources. So not to prepare for the worst possible event happening once a year for all your hours of the year, and also taking into account that when you have lower levels of wind and solar, then you don't also have so much uncertainty. For the generation capacity adequacy, or generally the capacity expansion and the generation mix of your future system, so these kind of simulations are needed for either for the consistent future scenarios, but also often you ask a specific question that how much capacity value wind or solar actually has on your system. And here we also have already very clear recommendations on the methodology, because we have this ELCC method, the effective load carrying capability method, that has already been recommended by IEEE before, and we also, our group thinks that this is the best way of capturing the impact of wind, or actually any addition to the power system. So you add a new generation resource, and then you check from long time series on your loss of load probability, and keeping that in the same level, how much load can you increase, and that is your capacity value then that you add to the system from the varying wind and solar. For here, as I already mentioned, the input data needs to be usually a lot. Of course, this can, if the wind and solar and load are all sort of following very clear patterns, you can be okay with lower amount of data. But for most power systems to get really robust results, you would need more than 10 years of data. The data is also quite easily available nowadays from reanalysis, the meteorological data. You just probably need to do some calibration for that. And then finally, for the production cost simulation, so this is really simulating or checking the flexibility. And this is usually simulated with what we call these UCED tools, Unit Commitment and Economic Dispatch tools. And there we do see that you often need either to do these iteration loops, so you check the situation and then you go back for your system management, or you go back for your generation mix or your network scenarios to really check that does your system have enough flexibility, and how does it work when you look at on an hourly level the operation of your system with the varying wind and solar. Here input data we we say that 1 year hourly data is what is sort of minimum requirement, but we do see actually that there several years would add robustness of the results. However, with already this amount of data, you will already capture quite well the results. And the recommendations here, we have quite many recommendations for this part, because to actually capture the impact of wind and solar, you need to model in your simulations all the flexibility that is available, but also the limitations to that flexibility to be able to really see the impact. And you also need to somehow model and simulate the impact of uncertainty, so also having the forecast errors simulated, and there we recommend, as seen in this graph, the so-called rolling planning. And this is because the load forecast errors do not change that dramatically from day ahead to hour ahead, but the wind and solar forecast errors do, or the forecasting increases in accuracy when you come closer to real time, and this is why you should somehow capture this. And one way of capturing this is to do the sort of rolling planning that you do first day ahead, and then you go 3 or 6 hours ahead, and then you use the updated forecast, and then you do update your dispatch also, and this will mimic more the real operation of a power system, but also take into account that the forecasting accuracy will be better and better for wind and solar. Here you should also use in your dispatch modeling the increased operating reserve targets that we were also discussing before. So here you can add some kind of dynamic reserve setting or reserve allocation. And then coming to the flexibility, limitations and constraints. So for the power plant, you really need to also model the minimum generation levels, the ramp rates, the part load efficiency to be able to capture the impact from balancing. And then regarding flexibility availability, so in future power systems, we do anticipate new flexibilities coming from power to X, like power to heat, from power to transport, like electric vehicles, storages, demand response, and also a way of operating your power system network, so the network limits having dynamic line ratings. To continue with the recommendations, you have a lot of possibilities for flexibility coming from interconnections, and this is quite a challenging part to simulate. So usually you would end up, if you have a big power system with many countries and regions interconnected, then you would need to somehow simulate, for example, your scope of study in high detail, but at least have something from also your neighboring areas modeled to really capture this right. But if you need to do, and usually you need to do some assumptions, you should at least then mention that are you over or underestimating the flexibility coming from using the interconnectors between the neighboring areas. And if we would go really into detail, we would ideally want to model the transmission network so that it's sort of n-1 secure. And here you may have the net transfer capacities of your lines more in your model, or have some iterative methods, and also methods somehow to take into account that there may be constraints coming also from the stability part. which I think leaves the floor to Damien to talk more about the transmission grid.
Hello, good afternoon. My name is Damien Flynn from University College Dublin, and I will guide you through some of the things that we have been thinking about in terms of recommendations whenever we look at the transmission grid and looking at some of the stability and dynamic issues. In general, I might say that whenever your wind share or your PV share gets beyond, let's say, 10 to 15%, then you need to start thinking about the network and the dynamics. So there are many aspects here to think about. So what we're really doing is displacing conventional synchronous machines with wind and PV, which tend to be based on power electronics. And that then raises various issues such as a reduction in system inertia and the impact on frequency stability, reduction in fault level, which gives concerns over voltage stability, a reduction in synchronizing torque and rotor angle stability, and then also concerns about harmonics due to the power electronics. One of the other things that wind and PV tends to do is that the wind and PV may be in different locations compared to the conventional generation. So as Marcus will talk about later, that brings out the importance of the distribution network. And there's also the issue that we may be building a lot of wind and PV very quickly. The network may not be expanded as quickly, so there may be issues in terms of congestion and local stability issues. It's also worth pointing out that as well as these developments in wind and PV generation, there are also changes in the load, which we shouldn't forget about. So the load as well is becoming more power electronic based. So if we're doing dynamic studies, we need to think about if the voltage changes and the frequency changes, how does that affect the loads? And we'll come on to that in a bit more detail later. We also need to think about that traditionally we had large generators which might have been far away from the load centers. With more distributed wind and PV, the distance between load and generation might be a lot closer. And also a thing that is happening in many countries is that large data centers are appearing. These tend to appear quite quickly, and there tends to be quite some uncertainty about the characteristics of these new loads and how they will interact with the rest of the system. So as a high-level methodology, Hannah talked about production cost simulation. That's a very important input to the sort of things that I want to talk about. That may include the network as part of that, which then leads into the load flow, the idea of working out the flows along the lines, working out the voltages at various points in the network, and then working out the robustness of the system to various disturbances, so-called dynamic analysis. So the sort of things that we might be looking at are transient stability, whenever there's a fault in the system, small signal stability, looking at minor disturbances, frequency stability, if, for example, we lose a large load or a large generator, and voltage stability, again, if there's a small disturbance, and what does the voltage profile look like. So scenario selection is an important task here, identifying what scenarios that we want to look at. So historically, people would have looked at high demand cases, low demand cases. On top of that, you might want to look at high and low wind cases or high and low solar cases. As Hannah mentioned, it's very important to recognize the correlation, that you can't just extract a case, let's assume high wind at the same time, let's assume high solar at the same time. You need to recognize the correlation between these inputs for your particular. That then leads into recognizing the likelihood of scenario occurrence, because if something happens quite often and it's concerning you, that implies that it's worthwhile investing time and cost into fixing that solution. If something is quite rare, then perhaps some simpler option might be more effective. In terms of dynamics, this also raises various options that you might want to think about. Reverse power flows, so that areas that were traditionally load centers might have lots of wind and PV, so that power flows in the opposite direction to normal. You might have storage on your system, so you might want to think about storage being full, the storage being empty. You might have low inertia situations, high inertia situations. I think one lesson that is learnt is that it's a good idea to go about a high-level scanning process. Therefore, rather than committing yourself to looking at particular scenarios, have a high-level scan of the various options that might be possible, and then that will allow you to identify potential problems, and then you can focus in on those particular scenarios. So an iterative process tends to be most effective. Just to illustrate this, this is showing the online inertia for the Irish system in a future case of 2020. Historically, you might have assumed that during the summer the demand is low and the inertia is low. During the winter time, say December to February, the load is high, the inertia might be high. But you can see, looking at this figure, that the inertia is quite variable across the year, and it's not easy to identify what are the high inertia periods, what are the low. In terms of the load flow, this can be coordinated with the unit commitment exercise. So you can make certain decisions like identifying must-run plant or locational plant, and they may help you with voltage support for the system. You can include a DC network to give you a general idea of what the power flows in the network might be. And then that means that whenever you come to the proper load flow stage, that you're not having sort of silly little problems because they haven't been considered unit commitment. So the unit commitment can actually give you a sensible and a robust system setup. Because we're looking at a future scenario, we shouldn't restrict ourselves to the present day system. So we might want to think about, are there advantages of including things such as dynamic line rating or new high temperature low sag conductors. We could try to make use of SVCs, STATCOMs, so on. But in the back of our mind, we're thinking about what is the likelihood of event occurrence, and hence, is it worthwhile investing large sums of money or large sums of time in actually solving these problems? So a probabilistic assessment needs to be part of the story. How often will particular events occur, and hence, how effective do my solutions need, or how costly do my solutions? In terms of the dynamics, modeling of the individual plants becomes very important. This can be a challenge with new power electronics, which can be quite difficult to find information about. But increasingly what is happening is that standard models or generic models are becoming available. And these generic models can be populated with specific data for particular manufacturers. So there's increasing confidence in the capabilities of these models. As part of this process, it's also worth remembering that we should also look at our models of our conventional generation and also of the load models. One of the things that we want to do in this dynamic modeling process is essentially test the limits of our system. And we may find that we haven't actually looked at those generator models or dynamic load models for a long time, and they may not be fit for purpose. So we should look at those carefully. So one example of this is the Western Electricity Coordinating Council in the US has proposed quite a sophisticated model for loads, creating motor representation, load shedding representation, and so on. This might seem quite complicated, but if I can give you a quick illustration of why you might want to look at your load models. So this is an illustration from the Western Wind and Solar Integration Study, and they applied a three-phase fault at a particular bus, and the blue trace is showing the response that the simulation reveals whenever you use standard models. And you can see that there's a voltage dip and then the voltage quickly restores and everything looks fine. But actually, whenever you use a more sophisticated load model, you get the red line, and obviously there's a very large difference between the red line and the blue. So the blue line is giving you false confidence of what actually might happen. As I said, generic wind and PV models are increasingly available, and manufacturers are involved in this process. So WEC and IEC models are available, which can be very valuable. It's worth playing around with these models in order that they match your particular system, so that they match grid code requirements in your particular system. So for example, you might want to look at the fault ride-through requirements. Typically these models do not include an emulated inertia capability, so you might want to include something like that. And they typically don't include things such as high wind ride-through. So there may be additional capabilities that you might want to. So this is just a quick representation of the high wind through capability. So on the left-hand side, you're showing a standard wind speed power curve for a wind turbine, whereby the wind turbine shuts down at high wind speeds, while on the right-hand side, you can see that the wind turbine is able to partially ride through the higher wind speeds. Just to illustrate how that might affect your conclusions, the red trace is showing what a wind farm might do under actual conditions. So you can see that for roughly a 6-hour period, the wind turbine is switched off, or the wind farm is switched off, and the blue trace is showing the response that you might actually get from a real wind farm. So it's able to contribute during the storm. We're focusing on wind and PV, but there are also other resources in the system that should be considered. So these are just some sample characteristics that you could create for, let's say, demand in the system, storage in the system. They can also add to the robustness of the system. And there are a wide range of additional scenarios that, again, could further be considered. I've listed a couple here. I'm just going to focus on the second one briefly, voltage dip-induced frequency dips. And if I can explain what that concept is. So on the top trace, we're showing the nodal voltage, so a fault has been applied. Bottom trace, we're showing the response in red of a conventional synchronous machine, and you can see that that conventional synchronous machine produces its output during the fault, but recovers quickly. And the green trace is showing what a wind turbine might do, so it has a slower recovery. And the blue area is showing that there is going to be a lost energy area. So there's going to be a power imbalance due to the initial fault. So if we have a scenario such as in the map of Iberia and looking at a fault in Portugal, and you can see that the blue is representing the voltage dip. So if we had lots of wind turbines or PV panels in that area, they could see this voltage dip, and there could be a large drop in the power output from the wind or the... This figure is just illustrating that. At 1 second, we have had a fault. That has led to a voltage depression in an area, and you can see that we're seeing a roughly 3,000 megawatt power imbalance in some scenarios. So looking at that in a bit more detail, so a number of scenarios have been shown for the Irish system, where again a 3-phase fault is considered. And ideally, what we're looking at here is the rate of change of frequency on the y-axis and the frequency nadir on the x-axis. So ideally, we would like to be in the top right-hand corner, but you can see that there are lots of points beneath the green line and also on the left-hand side of the figure. So that looks a bit concerning, but part of the reason we're seeing these problems is because the distribution network hasn't really been considered in full detail. So if I look at some revised simulation results, we can see that a lot of the points have moved towards the right-hand side. So yes, still we have problems, but by increasing our representation of the distribution network, we're actually getting a better picture of what is going on, and the results are not as severe as we perhaps first thought. So in conclusion, so the messages that I would like to say is that there's a trade-off between planning and operational policy. So our stability analysis and our load flow analysis is not just a one-shot analysis that we define our scenarios, run simulations, we get results. It can be that we run our simulations and then either we might say that we're looking at the wrong scenarios, we need to focus in on particular scenarios, but we also need to think about can we make changes? Can we improve the controls on our wind turbines or PV plant or on the conventional plant? Can we look at adding some network devices? And those might mean that at low-cost solutions we can actually solve some of our problems quite easily. As a final point, we're looking at various forms of stability. It's not straightforward to say that certain forms of stability will apply. It can be very system specific. Perhaps a general observation is that in smaller systems or island systems, perhaps frequency stability is a bigger issue. In larger systems which are more interconnected, then perhaps voltage stability and transient stability is a bigger issue. But one thing to highlight perhaps is that wind turbines, PV, shouldn't be seen as presenting problems to your system. Wind turbines and PV controls give you a lot of new capability that you didn't have before. So instead of saying, what are my problems whenever I add wind and PV, perhaps the question that should be asked is, how can I take advantage of these new control options to improve the stability of my system? So with that, I would like to pass over to Marcus, who will talk about the distribution system.
Yes, thank you, Damon, very much. Also, good morning, good afternoon, good evening from my side. My name is Marcus Kreitschi. I'm a founder of IEAWIND in Germany, and we provided this chapter here on distribution integration studies in cooperation with Barry Matter from NREL. And in contrast to the previous chapters, we focus here very strongly on distribution challenges, and we just provide here a very brief overview on that. At first, I want just very shortly go into distribution grid modeling, because I think this is one of the major challenges if you do comprehensive distribution integration studies. So compared to transmission level, we have kind of scarce input data. Sometimes you don't have the grid models available, measurement data, and so on, high complexity and high regional diversity of the distribution level. And in the report, we provide here best practice examples for different kind of distribution study objectives. But overall, the methodology you use for grid modeling depends on your objective and also on your available data. Just want to highlight here for grid modeling in statewide or system-wide integration studies, so here we are talking of thousands or 10,000s of distribution feeders, you have to somehow reduce the kind of complexity of your studies. And one very typical approach is analysis of representative grids in detail. Then you have some statistical methods to give an estimate for overall power system, and here quite important is clustering and taxonomies of feeder. And here also I just want to highlight that the report of taxonomy of distribution feeders from IEA PVPS will come out within the next month. So overall, we see that data acquisition, data handling, and distribution grid modeling is one of the major challenges. And if you do system-wide studies or statewide studies with a lot of grid, you really have a high need for automation in your processes. How to gather data, how have interfaces here available with a quite high automation. So this may be the point on that. In the report, we provide also a brief overview on different kind of objectives of distribution grid integration studies and some best practice example. But overall, these methodologies are quite fast evolving and quite dynamically in the distribution level. We have wind PVs coming, electric vehicles are coming. Now we're starting with smart grids, smart meter rollout, so distribution grid planners just getting to know their grid in detail. And so here, quite dynamic development. We can see in the report we just highlight different kind of objectives of distribution integration studies. First one is hosting capacity analysis, where you look how much wind and PV you can interconnect with your system without the need of any grid reinforcements. Then we provide a short overview on distribution network reinforcement analysis. So you maybe here you already reached your hosting capacity and look how you can increase your hosting capacity in the grid with suitable measures. Then we have voltage variability analysis. We have here small areas in distribution grid sometimes and a high simultaneity of wind and PV. So you have very high variability of wind and PV, and also especially with the voltage. And here we have to look how to control voltage regulators. Just as an example, grid losses analysis also quite important and getting more important here, and we see also that wind and PV is strongly affected, also the grid losses, and here also new methodologies need to be provided. Further objectives, of course, protection, harmonic studies, flicker studies have also been done, but they are not in detail here discussed in the report. In the next slide, I maybe just will give a very short overview on the first 2 points, hosting capacity analysis and network reinforcement, but I think they are most related with grid adequacy. Here, hosting capacity analysis, I think distribution people are quite aware of that. You analyze the maximum amount of wind and PV interconnections in the grid without any need for reinforcement. It's a fast screen technique. I can shortly explain this on the picture on the right side. And it's also a benchmark of mitigation methods here to avoid grid reinforcement. For example, you apply volt bar control and check your impact on the hosting capacity. In the report now, I just want to highlight shortly deployment scenario independent hosting capacity analysis, which is quite helpful if you have, for example, rooftop PV, small residential systems where you don't know where future systems will be interconnected. So you can do Monte Carlo simulations running thousands, maybe 10,000 of different deployment scenarios here in your distribution grid, and the output can be a scatter plot like you can see here on the right side. You see that the voltage rise in the feeder increases with increased PV penetration, but what you also can see that if you're below 0.5 NV, for this example, you don't have any voltage issues. So if you're a grid planner, just for an example, you have to interconnect the PV systems, you maybe have to do that for a couple of hundred feeders. You see, okay, below 500 kV, I don't have any problem, so I can interconnect the system, and this is a typical fast screen method here in the distribution level, and I think here the work by APRI and Annual is already quite advanced on this. On the next slide, I'll shortly describe distribution grid reinforcement analysis. It's something we have done a lot in Germany, because here PV, wind kind of have to be interconnected to the power system by the distribution grid operator or transmission grid operator if it's reasonable, and it's a benchmark also for different kind of grid integration measures. And also policymakers here wanted to know how much does it cost to integrate PV, wind, electric vehicles into the power systems, and what we maybe have to adopt in our regulatory requirements. Best practice example are some recommendations from our side. You need a kind of very comprehensive catalog of grid planning measures. You should consider grid optimization before grid reinforcement, before grid expansion. So you have a lot of options here. You can do parallel lines, add additional transformer station, additional voltage regulator, volt bar control, and so on. There's also an approach where you see that automation also in distribution grid studies is getting more and more important, because we're getting more and more options. We see here in this kind of study different kind of input data. It depends, like I said before, what you have available. Representative grids or actual real grid data, which is used in this kind of studies. And I think what's also important is what we also see that's not always been done is if you analyze how much grid reinforcement you have to do in a distribution grid, you have to put it in contrast with generally required reinforcement, because of outdated grid elements, old lines you just have to replace, and you have to put this in contrast with that. Yeah, finally, that was just a very brief overview on that. For modeling and data handling, we see that best practice of distribution modeling depends on the detailed study objective and available input data. Data acquisition, data handling is still a major challenge, I think, in the distribution level. We see here a high need for automation of interfaces and exchanging data and information for this kind of study. Scope and methodologies are still developing, and we are, in most cases, let's say, not that far, like in transmission studies. So I think well-established best planning examples still have to be developed for some kind of cases, but for example, like hosting capacity, I think we are quite advanced on this. And finally, I also just want to highlight the importance of transmission distribution coordination. Damien already talked about it, so here one example is the development of dynamic grid elements, like Damien explained, and just also want to highlight that we also have a report on TISO cooperation, should come out within the next weeks within the IEA PVPS task. So I'm so far done with the distribution chapter. Hannele?
Okay. So then to conclude, so after these green boxes in the flowchart of making all the simulations that you have had in the scope of your study, then when you first check that if the results are okay and whether you need to do them again with these red arrows of iteration. So basically you will then finally come to this data analysis and conclusions about your study. So what we want to highlight here is that the iterations really provide significant insights, that when you go back from your simulations to checking if your generation mix, if your transmission scenario, if your operational practices are okay, or if you would like to modify them, this is a very good thing to notice. And then generally, often when you try to extract some impacts that wind and solar have on your power system operation, then you usually need to have a base case where you compare your results so that you can see that, okay, this was the impact of wind and solar. However, what we have noticed is that the base case selected is very challenging, and actually we even cannot so far directly recommend any clear base case when you have a higher share wind and solar system. So when we started 10 years ago, it was a lot about integration cost estimation, and again, we have it in some countries that this is relevant, this question. However, we have not found a recommended method to actually draw an integration cost number from these simulations. It is extremely difficult to be found for a single technology. So basically, what we recommend is that you would have different future scenarios that have a similar reliability, and then you should compare all what is there, but also then, of course, also the benefits that wind and solar bring in reduced emissions. So we also give some recommendations of what to present in your final conclusions. For example, the share of wind and PV is often a bit hidden in your studies, and to be able to compare with other studies, that would be an interesting thing to have there. For the future work, for the flexibility needs, we already have a couple a direct flexibility tools and metrics available, but this is still an evolving field. The uncertainty and the network constraints, how to take them into account in the production cost simulation or the unit commitment and economic dispatch. That is one thing that is evolving now. And generally, how to set up the simulation cases to extract impact and potentially also costs in future. This is something that many places are working on, and what we do see, since wind and solar have become like even a backbone of future systems, future renewable systems. So we tend to see that there is a move from the initial question of cost of integration to a future system question of what is the cost of inflexibility that you start seeing in your future systems when you want to have them as renewable as possible. And then also the grid part, especially the stability part, and also the DC grid part is evolving, and the implications of market design is also an interesting field of work. And I would like to just conclude by recommendations that please do use the recommended practices checklist for benchmarking your study. So in the executive summary, we have just a list of bullet points for all these recommendations that we have now presented. And we hope this would be an accessible way of seeing your study, how you are doing it, because all studies need to do assumptions and have their limitations. So we hope that this benchmarking list, bullet point list, could be used to also check what you have done and what are the assumptions that you have had to make, and also help you in presenting your results. Or if there are people who are actually reviewing some studies, also in those cases, this should be a nice way of using this work. So the report is available, this edition 2 from 2018, and then there is an older report only looking at wind, not looking at distribution grid at all, and that was from 2013. So the latest report is also now available in the websites that we provided. Yes, I think that's it. If you are interested in this collaboration, you could also contact us through the web pages for PV and wind integration.